Now I'm going to go through an example showing all the steps that I talked about during the first part of the class. You'll remember that those steps were developing your code on Biowulf, compiling that code, writing and executing swarm files, and finally monitoring your job. So in order to be able to develop your code on Biowulf, you first have to be able to get on Biowulf. So I'm just going to start right from the beginning and show you how to do that. So I'm just going to go ahead and open up a web browser. I'm going to navigate to hpc.nih.gov. And once there, I'm going to go ahead and look at how to, and then I'm going to navigate here to connect to Biowulf. And that's going to bring me to this nice web page, which is going to give me different methods for connecting from Windows machine, Macs, Linux, etc. And I'm going to show you what's currently the preferred method for connecting to Biowulf for both Linux, Mac, and Windows, and that's going to be this no machine NX. Okay, so if I open this up, it's going to give me a lot of information about how to install. Let me make that a little bit bigger. It's going to give me a lot of information about how to install NX, how to connect to the systems using NX, and so on. I can go ahead and just click on No Machine's website. It'll take me here where I can download and install it for whatever system I'm on. But I've already got it installed, so I'm going to go ahead and fire it up. And I've got some connections that I've already established here. I'm going to go ahead and pretend that I have not established any connections which are already saved, so I can take you through the steps of establishing a connection for the first time. And I'm going to do that to Helix. If you are on the VPN or if you are on campus, you can of course do that to Biowulf or another server, but I'm just going to go ahead and go to Helix because you can do that from anywhere, and then from Helix, I'll show you later, you can actually get to other servers and go through Helix to get to Biowulf. Okay, so I'm going to pretend I don't have this connection here. I'm just going to start a new connection. Protocol BSSH. Host name is going to be helix.nih.gov. It's going to be port 22. I'm going to use the no machine login. This is different than what it would be for other systems if you were connecting directly to Biowulf, or if you were connecting directly to another HPC at NIH system, you would use the system login. But since we're connecting to Helix, it's going to be the no machine login. This is not for us. I'm not going to use a proxy, and I'll call it this to differentiate it from my session, which is already on my session that I've already saved. I'm not going to create a desktop link, and so this is the new connection that I've just initiated. So I'll double click on that. Enter my username, password. And then I'm going to be presented with several options. One thing I could do is I could create a new custom session, and what this will do, instead of giving me an entire desktop, it'll just open up a terminal, and then in that terminal I'll be able to type whatever commands I want, and if those commands correspond to programs that use the X Windows protocol, then they will just go ahead and automatically open up the graphical user interfaces. However, so this is nice because you can have like an undocked session of MATLAB or whatever it is that you're running. However, I found that it's actually slower. I don't know if that's just me or if that's actually something with the protocol. Some of the other ones here don't work. So really creating a new GNOME virtual desktop, GNOME is installed on our systems. It's, I think, the default desktop for CentOS, which is what we're running. So just going ahead and creating one of these is the way to go. Sometimes it takes a minute to fire up. One of the great things about NX actually is that it tries to optimize a lot of things for speed. So it does that by extensively caching everything it possibly can. So you'll notice a lot of times the first time you do something, the first time you click on maybe the applications menu and open up a particular application, for instance, or something like that, it takes a while, but then when you do it again, it moves really rapidly, and that's because it's cached that action. And it's just going from the cache. So let me go ahead and maximize this. And this is one of the problems that a lot of people run into sometimes is they maximize it, but the screen kind of remains small. So one thing you can do, go up here to the upper right hand corner and there's a little peel down menu that you can get. Go ahead and click on that. And that's going to take you to all these options. Click on display, and what you want to do is resize the remote screen. Okay, once you're done doing that, this might take a second to do that, but then it will resize. And this is taking a little longer than it normally does. Okay, there we go. So there might be an excessive load on Helix right now. It's kind of that time of day. Okay, but in any case, that's how we can establish a X Windows connection to Helix suitable to start running MATLAB. Okay, so now I'm on Helix. That's great, but you recall that we want to run the code, or we want to run MATLAB on Biowulf, and we want to ultimately submit our swarm jobs from Biowulf. So what now? Well, it's a little funny, but even though we just started this interactive session, the first thing you want to do after doing that is to start up a terminal. And I'll go ahead and use that terminal to SSH to SSH to Biowulf. Okay, so now I'm on Biowulf, and so it might be your knee-jerk reaction now. The first thing to do is just go ahead and fire up MATLAB, but you'll see that Biowulf, doesn't want you to do that, or doesn't know what MATLAB is yet. And you might say, "Oh, yeah, that's right. I need to load my module so that Biowulf knows what MATLAB is, or knows where MATLAB is." And then you're going to get this error telling you that you can't run MATLAB on the Biowulf login node because that's just a computationally intense process. So then you'll say, oh yeah, that's right, I forgot I have to allocate resources. Okay, so remember that the sinteractive command is the command for allocating resources, and I've got these arguments already saved where the resource, I'm going to go ahead and just take the default number of CPUs, the default amount of memory, and the resources that I'm going to ask for are the MATLAB license, the MATLAB stat license, and the MATLAB image processing license. If you wanted, let me go ahead and maximize this. If you wanted to load some other, to allocate some different types of resources, say you're going to need a little bit more memory. Your jobs keep dying because once you try to load one of your big map files, you run out of memory and then MATLAB dies, and you can't remember how to do that. So if you start to run into trouble, you can't remember how to allocate resources, just remember you can use that -H option, and then you can start looking through and saying, okay, well, I could allocate more CPUs. That's not really what I want to do. Let's see. I can give myself more time, but that's really not what I want to do. I want to, it's probably right in front of my face. I want to allocate more memory. or conversely, if I want to do a little math, I want to allocate more memory per CPU. Both of these are, going to give you the same result with MATLAB. Okay. Also, it came up earlier in the class during the lecture. How do you know? How do you know what the short names of the licenses are that you're supposed to be allocating? One way to kind of get at that is to use the licenses command. So licenses gives you the state of the licenses on the system currently. You can use licenses with the dash verbose option to see exactly how many licenses are allocated on each of the systems. And you can use it with the -H option to get help, and that's going to give you the short version of all these different toolboxes. It's still a little bit more complicated than that, because some of these toolboxes Slurm actually doesn't know about, and that's because we don't require people to check out licenses to use them on Biowulf. The reason for that is some of these are not really very popular toolboxes. You can use S-control, show license, and that's going to show you which of these licenses actually have to be allocated on Biowulf. But another thing you can do is you can just go to the website. So I'm going to bring a browser back up, and let's see, go to applications, and then you go to MATLAB. Scroll down here, just on the main MATLAB applications page. It'll give you, you can look here and you can see all the licenses, and then you can see which licenses it's required that you actually check out on Biowulf. This is really the authoritative source. So if I'm going to use the image processing toolbox, then yes, I do have to check that license out on Biowulf because there's no dash, and it's MATLAB-image is the short version. If I want to use, let's see, if I want to use the compiler, we've actually changed this since I spoke earlier in the class earlier. If I want to use the compiler, I actually don't have to allocate that resource on Biowulf anymore, and that's because MCC is doing such a good job of managing those licenses that I don't need to allocate it like that. Okay, so that's how you can get that information about what licenses you should be allocating. Okay, so I know that based on my job, these are the licenses that I do have to allocate. And so I'll just go ahead and get this job going. So now what the Biowulf login node is doing is it's looking all the way throughout the cluster, and it's finding, where can it find me those 2 CPUs? Where can it find me the 4 gigabytes of memory? Does it have these licenses available to give me? And once it gets all those things squared away, then it'll give me a node and put me on that node. And so now you can see I'm on compute node 1650, wherever that is. So you might be tempted once again to go ahead and start MATLAB, but obviously you can't do that. So, that's right, we have to load our module. And if I just go ahead and put a slash here, and I hit tab a couple times, maybe a few more times, then it's going to go ahead and give me all the different module files that it has available. So these are the different versions of MATLAB which are currently installed on the system that I could start. But I'm just going to take the default, which in this case is going to be 2015B. That's loaded, and then I'm going to go ahead and start MATLAB. Real quick before I start, well, actually no, I'll just go ahead and get it started. I'm going to use this AND switch, or this AND argument, and that is going to allow me to continue to use the terminal while MATLAB starts. Sorry. And then you'll notice that we got this little annoying warning here that says that MATLAB is selecting software OpenGL. And what that is, that's actually, it could be important for you depending on what it is that you're trying to do. So later versions of MATLAB, I believe starting in 2014B, the MathWorks overhauled the graphics engine for MATLAB. You might have noticed if you've been using MATLAB for a while, you might have noticed that when you updated, the appearance of your figures changed. Well, a lot more than that actually changed under the hood. And so sometimes using those later versions of MATLAB, certain figures won't render properly, and they might even cause MATLAB to crash if you try to plot them. And this might be things like three-dimensional figures, for instance, or really big images. So the way to get around that is when you start MATLAB, start it up with the following options. So it's going to be MATLAB, OpenGL, Hardware Basic. But the trick is, this doesn't work currently on Helix. You have to have a direct connection to Biowulf to have this working. So you would have to either be on campus or you'd have to be using your VPN. And if you're doing one of those two things, then you can go ahead and issue this command, I guess with the ands, that you can continue to use your terminal if you want to. And then once you've done that, then you can go ahead and plot really kind of intensive things without worrying about MATLAB crashing. Okay. So before I leave the terminal here, I'm going to go ahead and copy the data to my data directory. So this was the command that I was telling you in the class to issue. Okay. And now in MATLAB, I should be able to CD to that directory, the one that I just copied. And it's there, and I've got the files that I expected to be there. Okay, so now I'm ready to start going through the example. Okay, so that's pretty much the first step now. We've we figured out how to get onto Biowulf and to start developing our code on Biowulf, and we're on a compute node, and as you can see, I've already developed some code here. So if you look here, I've got a couple of directories, and then I've got some M files. So let's have a look and see what's in those directories. So if we look in View Images, got a couple of JPEGs here in this directory. And if we look at lots of images, we got lots of images. We got 300 pings. So you can imagine, you're probably already getting the idea that I want to do some image processing. So let's say that I've developed, an algorithm that I think is really great for doing image processing. And so here's an M file called kmeans image.m, and let's have a look at that and see what that does. You can see here that it takes as input a file name, and then if you look down here, it's got some optional inputs. And what it actually does is it reduces the number of colors in an image. So it might help if I kind of show you. So let me say that a file in equals few images. So I am going to analyze the penguins JPEG, which is in View Images. All right. So one of the things that you should notice right off the bat is that this algorithm is not very efficient. It takes kind of a while for it to analyze the images. And so while it's doing that, well, I'll go ahead and sort of explain to you what it's doing. So if I don't give it k clusters as an input, then it's just going to default to 3. And what that means is that I want it to give me 3 different colors for my different in my new analyzed image. So this is the input image over here. This is the one that I just loaded, and then this is the analyzed version. We can see that it downsampled the colors down to 3. And so the way in which it does that is kind of interesting. It actually takes each pixel, and each pixel, on a monitor has 3 different values: a red, a green, and a blue value, RGB value. K-means image takes each one of those 3 values, and it projects each pixel into 3-dimensional space, making a big cloud of pixels. And then if you say, I want 3 clusters of pixels, then it will use a fitting routine to try to segment that cloud of pixels into 3 different clusters. Or if you give it 5 or 7 or 10 or whatever, it'll use this fitting algorithm in order to parse your cloud of pixels up into that many different colors. So it's actually kind of an interesting algorithm. It's a machine learning algorithm, but it's actually overkill for what we're trying to use it for here. Let me just give you a few more examples. I'm going to analyze the penguin's JPEG again, but instead of asking for 3 colors, now I'm going to ask for 6 colors, and I'm going to go ahead and do that 3 times. Okay, so now you might be kind of scratching your head wondering what's going on, because in these instances the algorithm didn't even converge to the same answer. So I ran it 3 times with identical input, and in one of these instances the clustering algorithm decided that yellow was one of the 6 colors rather that it should parse this image up into. And then in another instance, it said, well, I shouldn't use yellow, and I should only use 2 different color values to represent the sky. And then in this example, it used 3 different values to represent the sky, and once again, no yellow. So you can see that this algorithm has some randomness to it. It doesn't always replicate. And that's because the way the algorithm works is that it begins at several random points, and then it works from there iteratively in order to try to come to the best solution that it can possibly get to for however many colors that you give it. But it might settle on a local minimum instead of a global minimum. So one way around this is to give it more repetitions and make it, oh, wait a minute. One way to get around this is to give it a 3rd input, and that's going to say, instead of just doing this once every time, try to do it 3 times or 15 times or 10 times or however many times you wanted to do it in order to converge to the best global minimum. And when you increase the number of times, what you're doing is you're increasing the number of random starting points that you give to the algorithm, and you increase the likelihood or the probability that one of those repetitions is going to land on the global minimum instead of a local minimum, and it's going to produce the best possible result for you. So, but as you can see, including increasing the number of repetitions, obviously has some drawbacks. It takes longer, it takes a longer amount of time to come to the solution when you increase the number of repetitions. So that's a pretty major drawback. Okay, so hopefully we'll see that in both these. Well, that didn't work. So evidently 3 repetitions is not enough. We'll have to go even larger than 3. And you can see that already that took kind of a while. So this is not a very efficient algorithm. Just for completeness, excuse me, I'll show you also. Let me do a different picture actually. So So just for completeness, I'll show you what this final input does. Let's do 20 colors, and I'll just take the default 1 repetition, and then I'm going to name this image, test image, and I'll turn it into a ping. And so what this is going to do is it's actually going to save the image after it's done analyzing it. And since I gave it a different file extension, it should convert the image from a JPEG into a ping. Since I didn't give it a location, it's just going to use what my current working directory is, so we should see that pop up over here. And so you can kind of get an idea now that you know that there are a few images in this directory and lots of images in this directory, you might be able to get an idea of what it is that I'm going to be trying to do. So this algorithm takes a really long time. I've got a lot of images. I want to analyze all of them. You know, time to start using parallel computing. And just as an aside, this is my dog, General So. You'll be seeing more of him later on in the demonstration. Okay, I actually have the data drive mounted, so I can go down here to the swarm example. So this is the same place that I am right now in MATLAB, and here's that test image I just made. Okay, and there it is. So it saved the analyzed image. Okay, now once again, let's say I want to analyze, so you know, let's say I want to use this, even though this algorithm is not very efficient and it's got some drawbacks, let's say I want to use it to analyze a lot of images. And in fact, let's go even further and say that I don't want to just use it to analyze a few images, but I want it to analyze frames of a movie. So that's actually what's contained here in my lots of images folder. Well, it's going to become important if I want to analyze the frames of a movie that I'm able to replicate, or I'm able to analyze each of the images sequentially in kind of the same way, that I don't drop into local minima, because you can kind of start to think about what's going to happen if I don't converge on a very good solution every time I run the algorithm, and that's going to be that the movie's going to be kind of flickering, and it's going to, you know, not look very good. The colors are going to be bouncing around. So I really want to make sure that I you know, get a good answer every time I run this algorithm. So let's have a look really quick. I'm going to look at lots of images, 000.ping. That's the first one. You'll remember there's 300 images in that directory. And I'm going to see how long it takes to analyze it, looking for 7 colors and 15 repetitions. And I want to time that. So I'm going to use tick and tock in order to time that. And so you can already kind of see that, you know, probably what I want to do is I want to analyze all of the images in this lots of images directory, not serially, but I want to do so in parallel. And then I want to save the analyzed images, you know, using this file out argument, you know, maybe in a new directory or something. And then I would like to ideally have a function which will go through all of those images and piece them back together into a movie, you know, when the job completes. So that's kind of this example. I'm going to have 2 jobs, one that runs first in parallel, and then a second job that runs after the first one, and you know, is just a single command which is going to run with a dependency which is going to take all the images once they're analyzed and piece them all back together into a movie. And this is the kind of thing that you know, you might do quite a lot. Have one job run, another job run afterward, and then maybe another job even after that, run with a dependency. And it's also quite often that researchers will run jobs where they've got a whole lot of files to process, and they just, the way that they break the job down and do it in parallel is just to process all those files at the same time. Okay, so here's another shot of my dog. This is the first frame from the movie that we're going to be analyzing, and so you can see it took a little over 60 seconds. So just to think about that for a second, we know that there are 300 frames in this movie. So if it's running at 30 frames per second, we've got 10 seconds of this movie. If it takes 61 seconds to analyze each one of those, it's going to take us this many seconds, or 305 minutes, or a little over 5 hours. So I don't usually like to wait for 5 hours for my analysis to get done. It might not be such a big deal for you, but if you think for a second, this is just to analyze 10 seconds worth of data. 5 hours to analyze 10 seconds worth of data. So let's say instead of just 10-second movie, we had a full feature-length film. Okay, so that would be 2 hours times 60 minutes times 60 seconds. So that's how many seconds are in that film, and then let's say it's running at 30 frames per second, so that's how many frames would be in the entire film. And so then if it took each one of those a minute to analyze, then we're looking at that many seconds, or also we're just looking at, once again, that many minutes. That means this many hours. That means this many days. So that's a long time to wait if your computer decides that it needs to update, or if your code has a bug, or if you decide that you didn't like the number of colors that you selected. So you can see how parallel computing can really enable you to do things that it's not just a convenience, it really enables you to do things that you wouldn't otherwise be able to even attempt. Okay, so just to kind of round all this out and let you know once again where we're going to be going, we're going to use this k-means image M file, this function, to analyze all of our files in parallel. And then after that, I'm going to start this other function with a dependency called dir to AVI, or directory to AVI. And this function takes as input a directory, and then as optional input, actually they're all optional inputs, so if you don't give it any input, it'll just look at where it's at, where its current working directory is, and it will assume that there are frames of a movie there somewhere, and it'll try to find them and piece them all together. Or you can give it a different input and it'll go and look for frames of a movie elsewhere. I'm not really going to go through either of these M files in detail. You can look at them on your own if you like. But now that you know that I'm going to compile this code, I do want to point out to you some of the things that I talked about in the first part of the class. So here you'll notice that every time I ran that code, I had these little figures that popped up. Obviously, I don't really care about those figures popping up when I compile my code, and actually that can actually not be a helpful thing to have happen. So here I've used that is deployed switch that I talked about in the first part of the class. So these figures will only be made if this code is not deployed, that is, if it's not compiled. And then I anticipated the first input we have here is supposed to be a string. And once again, once it's compiled and we call it from the shell, it'll end up being a string, and that'll be just fine. But the second input is supposed to be a double. So I anticipated I was going to compile it, and I put this test here. If k-clusters is char, then eval sprintf k-clusters equals the contents of sprintf. So that's that little trick I showed you, that this is going to convert the char back into a double. And file out is kind of a funny one. I actually said that the user could have supplied the empty set, and I just kind of did that to show you this is a little bit different. So now, if from the shell I supply 2 brackets indicating the empty set, well, that's great. That's going to come into this function, and this function is going to see 2 characters, right? It's going to see a string, and a string is not an empty set. So then it's going to the way I've got this set up is that if not is empty, that input, then it goes ahead and it saves the file. Well, in this case, we're going to have an error because it's going to say that's not empty. You know, the empty set is not empty, but the empty set is also a pathological file name, and I haven't tried it, but I don't think it's actually going to be able to save it. So what this does is it says, well, if you've given me a string that is supposed to denote an empty set, then once again I'm going to use that trick to convert it back to its own contents, and that's going to fix that problem. Dear to AVI, also I've got the same kind of tests in place, so if is char frame rate, then convert that as if char size percentage. So these are things you can do. You can change the speed at which the movie runs, or you can resize the frames when you take it through this function if you like, and so those obviously should both be doubles, and so I've got those checks here. Okay. So the other thing that I told you that I needed to do to prepare, at least one of the other things, was I had to make sure that everything was on my path. So in the way in which, this is kind of like just really basic MATLAB, I'm not going to go in great detail about this, but the way in which you would do that is just say, which, I know that my k-means image calls a function called k-means, obviously. There it is. So just to make sure that's on the path, which k-means, it's in the statistics toolbox, which I saw reshape there is something I use. So that's a MATLAB built-in. So it knows where these things are. If I said which, let's say I had something in here called some function. Oops, I misspelled it. Either way, it doesn't know where it's at. So if I did have a function that wasn't on the path, I would have to, let's say it was in one of these directories, I would have to go over and I could right-click on it, and I could go down here to add path, and I could select that, or I could go up here to my path tool, I could set the path here, I can bring up this GUI, or I could use the path function. That'll give you information on how to use the path function. And finally, if I could also write a startup, I could write a startup file that included my path, and I could put that in my MATLAB directory, in my home directory, so that would run every time that MATLAB started, and that would set my path up. So all the functions that I thought were important that I write are always on my path. So this is just kind of like basic MATLAB stuff. Actually, kind of a surprising number of people don't really set their paths up, and they rely on either adding paths in the functions or CDing to different directories, you know, which might seem like the right thing to do, and maybe is the right thing to do outside of MATLAB, but within MATLAB, you're going to run into problems if you try to compile your code and you don't have everything on the path. Okay, so that's basically step one. So I've developed my code, and I've you know, prepared it all for compiling, and in the remainder now of the examples, I'm going to go through the remainder of these M files, which are actually not for analysis, but they're actually set up just for running, for compiling, for essentially for going through all the rest of the steps that I talked about in the first part of the class, compiling the code, building swarm files and executing those swarm files, and then finally monitoring the data, or monitoring the jobs once they've been spawned. So let me go ahead and bring up the script that kind of controls all of that. It's called par k-means image, or parallel k-means image.m, and so for the remainder of this example, we'll be going through this. Alright, so now let's just go ahead and start looking at the code that will actually be used to run these jobs in parallel. So in order to do this, I'm going to run this code in debug mode. If you're not familiar with debug mode, this is a really excellent tool that you should really start using. So I'm just going to throw a breakpoint up here, and I could press this run button to run the code, but instead I'm going to use F5 just to let you know. And then as we go through this code, instead of going up here and clicking, continue and step in and step out, I'm just going to use F10 for step, F11 for step in, Shift F11 for step out, and then F5 for continue. So you're going to see that, this is the point at which we are in the code right now, as indicated by this little green arrow. You're going to see that moving, but you're not going to see me clicking on anything. That's how we're going to be navigating, just if you're not familiar with debug mode. Okay, so let's have a look at this. So the very first thing I'm doing is I'm setting a flag here called recompile code, and I'm setting that to true. And so this flag down below is going to determine whether or not we actually compile the k-means image function and the dir to AVI function. So that's going to happen down here. So if I've set the recompile flag to 1, then we're going to enter this block, and we're going to go ahead and do the recompilation. I've set that as a flag because compiling code is time consuming and it consumes resources and licenses, and so if you haven't changed anything about your code since the last time you ran it, there's really no reason to recompile it. So we can just, if we run this again, we can just set it to false, and then everything will run a lot faster. Okay, then the first block of code here sets up all the variables which are necessary just to call k-means image. So you'll remember that k-means image has got some inputs. It's got the file that we're going to be analyzing, the number of clusters, the number of repetitions, and then where to save the analyzed file. So here, you notice I'm not giving it a file input. I'm actually going to be giving it a directory input. And then in my function where I generate my swarm file, I'm actually going to look in that directory, and based on what's in that directory, I'm going to make a list of all the files. And I'm going to use kind of like the same logic for the to save the files. I'm just going to give a directory in which to save the analyzed images, and then it's my function which generates my swarm file is going to be smart enough to know what names each one of those should have, but we'll get to that later. So this block just kind of sets up all the things that are necessary in order to run k-means image in parallel. We're going to ask for 7 colors or 7 clusters. We're going to want that to do 15 repetitions so that it can be replicated pretty easily when we're finished. And the input directory is going to be lots of images, which we already have. The output directory, which we don't already have, is analyzed images. So I'm going to have to make that directory, and that's done in the code below. The second block here sets up a lot of variables which are important actually just for calling the swarm. So these are arguments to swarm, and as you can see here in the comments, these are not all of the arguments to swarm. There are a lot of different arguments that you can supply. Here I'm just giving you some that users often want to use, some important ones. So I'm setting the amount of memory that I need. I'm just saying I need 1 gigabyte of memory per CPU. Recall that if I don't allocate that, it's going to give me 2 gigabytes per CPU. I want to run on the norm partition. I could set this to B1 or to quick or something else if I wanted to, but right now the norm will be fine. Processes per task. I haven't talked about this one yet. Processes, so recall that by default, if I don't specify the number of CPUs that I need, I'm going to get 2. And it's actually not possible, since the CPUs are actually 2 hyperthreads on a single core, it's not possible to be allocated fewer than 2 CPUs. Well, by default, I'm only going to have 1 task, one actual program running per core. So I'm going to be wasting one of those virtual processors, one of those CPUs, if I only run 1 process per task. So I could set this to 2 if I wanted to. And that way, on each core, I would actually be analyzing 2 images instead of 1. we'll see later on when we run this, that with process per task equals 1, the load is going to be 50%. If I set it up to 2, then the load would be 100%. It's kind of, with MATLAB, it's kind of up to you whether or not you actually want to do this. I've talked to some people at the MathWorks who suggest that you're actually not supposed to overload cores up to 100%. That, it's okay to put a little bit of extra load on a core, but MATLAB is kind of an intensive process as is doing other things, and so probably you don't want to go all the way up to 100%. But, you can do that if you want. That's up to you. If your jobs hang or if you have problems, then you might want to set this back to 1. I didn't really talk about this either, so we're going to be requesting some local scratch space. That is lscratch. We're going to be requesting 1 gigabyte of that, and the reason for that, this is a little bit different since I recorded part 1 earlier. In part 1 I told you that you could set an environmental variable to change the location of the MCR cache from your home directory to a local node. I've actually since found, in experimenting a little bit, that that method is not completely right, because if you have multiple processes which are running on at the same node, they might start to copy files to that MCR cache while other processes are trying to read from them, and you'll end up with errors. So instead, we have to do a slightly more complicated thing where we actually request local scratch space, and then in the swarm file itself, we're going to issue an extra command that I'll show you later on, which is going to set the MCR cache, and it's going to set the MCR cache to be unique for each job so that it's local and that each job has its own directory and they don't interfere with one another. So all that is to say that we're going to be using local scratch, so we need to tell Swarm that we need to use local scratch, so we need to ask for some amount. In this case, I'm giving it 1 gigabyte, which will be more than sufficient. The bundle option here, that's another one that you'll run into quite a bit that you might use. So the best way to understand bundling is to just have an example. So say that you've got 10,000 commands that you're trying to run as 10,000 jobs, and they're very fast. They run very quickly. Well, there's a little bit of overhead associated with allocating resources for each one of those jobs to run. So it can actually save you time if instead you run maybe 5 or 10 of those jobs serially instead of in parallel. And so the bundle option allows you to do that. In this case, I'm not using that, but you might want to turn that up to 5 or 10 or something if you've got a lot of jobs. It's also important to know that Swarm, if you hand it a lot of jobs, it will automatically bundle those jobs for you at some point. So I think that the limit is 1,000. If you go over 1,000, you're going to start to get automatic bundling happening. The time option, another important one, you should always specify a time. Anytime you submit a job, you should specify a time. The default time right now that you're going to get on the norm partition is 4 hours. The vast majority of jobs that are run on the norm partition actually finish executing much faster than 4 hours. And so if you just give it the default time, that's gonna it's gonna make your jobs harder to schedule, because the scheduler is going to think, here's this big job that needs 4 hours, and so it's going to think that it needs to hold on and wait to allocate resources until it knows that it's going to have some nodes available. That also puts a load on, it also kind of screws up scheduling for other people too. So if you don't need 4 hours, then you should definitely specify less. Here I'm specifying 5 minutes. But also your jobs might take more than 4 hours, in which case they'll be killed if they reach 4 hours and they're not finished executing. So you should, either way, you need to specify how much time you think your jobs are going to need. You can specify on the norm partition up to 10 days. And finally, I'm showing you here just as an example. This is just kind of one way to do this. I've got a variable that I'm setting to extra args, and I'll show you here down at the bottom how all of these variables are ending up being used and passed as arguments to Swarm. Notice that even the numbers, everything here is a string. So I've got one here called extra args, which you could just tack on whatever arguments you wanted at the end of this. You could keep on just building it and building it. And once we get down to the bottom, I'm going to show you how this argument just gets tacked onto the end of all the other arguments that you call and executes your swarm with whatever you put in there. Okay, so that's that block of code. And then here in this block of code, this is just essentially setting up a bunch of new directories. So I've got my directory where my code is here, and I've got a few subdirectories where I've got images. Once I start running this code, I'm going to end up with a lot of other stuff. I'm going to end up compiling code, which is going to give me shell scripts. I'm going to end up getting the swarm command is going to produce .e and .o files, which are going to have output and or standard error and standard output respectively. And I'm going to get one of those for every job I run. And I'm also going to have a bunch of analyzed images, so I don't want to just dump those all right here in this directory and mess it all up. So I'm actually going to make subdirectories. And so this block of code just says, you know, what are you going to name new files that end up being made, and what are you going to name, you know, these subdirectories? And it essentially just looks and says, you know, where are you at, and then sets up the directory structure according to where you're currently at. Okay, so after setting up all these parameters, now it's time to actually start running the code. So you'll remember step 1, which we've already done, is to get onto Biowulf and be able to develop your code interactively. And we've done that, and we've checked to make sure that all of our code is set up properly to compile properly. And so now we're ready to move on to step 2, which is actually to compile the code. Once again, we're only going to enter this if I've set the compile code flag to true, which it is. You can see it's a logical equal to 1. So the first thing I'm going to do here in the third block, I set something equal to a shell script directory, and I called it shell scripts. So here I'm going to say if that directory doesn't exist, which it doesn't right now, go ahead and make it. So we should see we now have a shell script directory here. And if the directory does exist, this line of code here will delete everything that's in it. So I'm going to make the directory, and then I'm going to make sure that it's empty. And then I'm going to go ahead and call MCC2. You can see that I'm using the functional version of this. Let me just go ahead and call it because it's going to take a minute to run, and then I'll talk more about it. Okay, you can see that I'm using the functional version of this call. You know what I mean by that is I've got parentheses here, and then I'm enclosing each one of my strings in single quotes. The reason I'm doing that is because I've got this you know, dynamically changing variable here, the shell script directory, and I'm using the -d option to send all the compiled code into that new directory. And so this might change because whenever you copy this code to your own directory, start running it yourself, I've got no idea what the root directory or what the parent directory is going to be. So this makes sure that wherever you copy this, as long as you're in this directory and it's your working directory, that's going to, you know, completely be fine, and it's going to send the compiled shell scripts to the correct location. You notice I've got 2 calls to MCC2 here. That's because I am compiling 2 different scripts, or 2 different functions. The first one is kmeansimage.m, and the second one is dir to avi.m. And I'm going to go ahead and call the second one. And you might notice that something interesting is happening here in the command prompt. Whenever I call MCC2, you're actually seeing MATLAB licensing information and version information popping up. And that's because what we're actually doing here, what MCC2 actually does, is it starts a brand new instance of MATLAB, and then from within that new instance, it compiles your code, checks out the license, does everything it needs to do, and then it closes that instance of MATLAB to ensure that the license is returned afterwards. So MCC2 is a lot more efficient at utilizing the compiler license than MCC is. Okay, we can watch if we wanted to. I've got that directory mounted. So if we go down here, you can see the shell scripts is now being populated with a lot of new it now has the k-means image, and it's got dir to AVI, and then it's got run k-means image and run dir to AVI, which are the most important files that we need. It's got these other files that we're not really going to use today. Okay, so that was step 2. So we've now compiled our code, and notice that we've done so in such a way that if we change anything about our code, no big deal. Whenever we run this again, we'll just set that flag to 1, and our code will always be up to date with the latest versions. Now we're going to move on to the next step, which is to generate and execute a swarm script. And so I've broken this down into A and B because you generate the script and then you execute the script. I've actually got C too because we've got a job dependency that we're going to run after this. Okay, so once again, I've written this code to try to be as flexible as possible. And, what that means practically in this case, I don't know when a user downloads this code to their local directory and they run it from their local directory, I don't know what version of MATLAB they're going to use to compile it. And so remember that first off, remember that we're going to give our compiled script a path to the MATLAB component runtime, and that's going to be the first input. And then second, remember that path is going to change depending on what version of MATLAB we use to compile our code. So this switch case statement just kind of sets all of that up for us, and this is kind of a nice way to do this. So I know that the root directory is going to be somewhere in user local MATLAB compiler, but I don't know what version we're going to use. So I'm going to query MATLAB with the version command here and say, what version of MATLAB is it? Right now I'm using 2015B, and so now I can use the switch case statement and say, well, switch MATLAB version. If it's 2015B, then the MCR, the MATLAB component runtime version, is going to be version 90, and then I can use that to make the entire path here. So now the MCR component runtime location is user local MATLAB compiler version 90. Okay, and then I've actually written a separate function here to make the swarm file. So, I've called it generate swarm k-means image, and then I'm giving it all these inputs, so it'll change the way that the swarm file is made depending on what inputs you give it. So I'm going to go ahead and step into this. Okay, and we can actually start to look at it. It's a little bit more complicated than what I showed you during part 1. And part of that complication is because I've written this to be very flexible, so that it can just it can be used as instead of just being a script that just always generates the same swarm file. You can hand it input, and then it's going to change the way that those swarm files are generated depending on what it gets. The way that this swarm file, or the way that generating this swarm file works, is that you're going to give it a directory location, and then it's going to generate down here a file list by looking in the directory, and it's going to look for whatever format you give it. In this case, I think that we're going to default to the format of pings. And so then once it's got that file list, it's going to run in a loop, setting up each command for each file that you're going to run. So let's go ahead and look at this. I think we're going to take some defaults here. K-clusters is something I should have handed it. Yes, that's going to end up being 7. This should be 15. Dir out should have a value. And then for format, we took the default of ping, because we happen to be analyzing a lot of pings. So the path and script, so the location and the name, I'm just going to put together here. I could have handed it that already put together, but this puts that together. So now this is the actual, run k-means image.sh script that I'm going to end up running. This is the command, and in part 1, I didn't actually give those commands the full file path, but here now I'm giving it the full file path, and that, it's a little bit more flexible that way. And then this string I'm just setting up. So this is a string that I've just got hard-coded here, and that's going to be the command that's going to set up the MCR cache, and it's going to use the slurm job ID, which is an environment variable, which is going to be unique to each one of the jobs in the job array. And so what that's going to do is it's going to make a new subdirectory on lscratch, and it's going to put the MCR cache in that subdirectory. This is the mechanism that I was talking about before, which is going to prevent jobs from interfering with one another. And so this command is going to end up here being prepended at the beginning of my command list. And I'll show all that to you here in a minute. It'll become more clear in a minute. Okay, once again, just in case. Oh, actually, no. So right now I've given this thing a double. That has to be a string, right? Because the command is actually going to end up being a string, so I need to change those to strings. And, you know, this is just for flexibility. We're not going to use this here, but once again, it's possible for k-means image to accept an empty, the empty set as input for the directory output. And so here, if we've given it the empty set, then I need to be able to set that up properly. So what this will do is it'll just convert that empty set to a double quoted string, which then can be used in the shell. Okay, I've got my file list. It should be 300 long. Yeah, so it's a data structure, and the field name within the data structure is going to give me each one of those file names. And now this part of the code is very similar to what I showed you in part 1. I'm going to initiate an empty command list, and then, you know, for II equals 1 to the length of file list, so for II in this case equals 1 to 300. The file in is going to be file list ii.name, so that should be 000.ping for the first one. File out, I'm going to prepend out underscore to that, so it should be out underscore 000.ping, and then I'm going to use each one of those files to build up this entire all these commands and stick them into a swarm file. Okay, and so notice this is a little bit more complicated because my current command, I'm putting here sprintf, and then it's just a bunch of blanks essentially. Then I'm filling in all the blanks here. So the current command is going to, let's see, I can kind of show it to you. It starts off, actually, let me just evaluate that real quick. So I just evaluated that, and that echoed that essentially here to the command window. So this is a sample command. The first part is export MCR cache root equals lscratch, and then the environmental variable, which is going to give us the job ID. This part is essentially telling MATLAB that when you start making this temporary cache directory for me, don't do it in my local directory, don't do it in my home directory rather, but do it on local scratch on the node, which is going to speed things up if I'm hitting that cache over and over and over again. The semicolon in the context of a swarm file says this is one command and this is another command, and since they're both on the same line, they'll both be associated with the same job. Okay, so the command is the full path and file name of my shell script, run k-means-image.sh. The first input is the location of the MATLAB component runtime, the MCR. Then I'm giving it the full path and file name of my first file. Of course, this is the first input to k-means image.m. The number of colors I want, the number of repetitions, and then the output, which is going to be in analyzed images versus lots of images, and it's going to be you know, out underscore and then the name of the image. Okay. Go back here. Right, and so that I'm just going to continue to add more and more of those commands, just one after the next after the next. Each one of those is going to be separated by a new line character. So we'll go down here, I'll press F5 to advance to the next breakpoint. We did all that. And then I'm going to open a file name, and the file name is going to be k-means-image.swarm. Here's its location. I'm going to open it in a mode that's going to overwrite it if it already exists. And then I'm going to use the handle here, the H, to fprintf to copy the command list into that file, and then close it. Okay. So what we should see now is k-means image.swarm, which we just built. I'm going to open that up in an editor just to show you what it looks like. And this is the first command that I showed you at the MATLAB command prompt just a second ago. Notice that it's the identical command for each job, with the exception here that the file name changes. So the same number of colors, same number of repetitions, but the file name changes. And similarly, the output file name, here changes as well. So you could, if you wanted to, you could structure this job in such a way that it only does one file, but it does, a whole lot of different combinations of colors and repetitions until you get one that you like. Or you could think of a million other things that you could do. But here we've just said we want to analyze all these files. Okay, so we've generated the swarm file. That was the first part of the third step. Now we're going to do the second part of the third step, which is actually to spawn the swarm. So once again, here I'm going to make a directory. In this case, it's going to be a directory for my .e and .o files, because I don't want to fill up my current working directory with all that stuff. So if not is directory, swarm directory, make directory, and if it already exists, once again, empty it. Okay, so now this is the command which is actually going to generate the swarm, and it's pretty complicated looking, but let me just break it down for you. So once again, we got our old friend here, sprintf, and that is going to build up a string based on all these escape sequences. So it's going to be bang, because it's a system command, swarm, -f for file name, and then -g for memory. So you can see each one of these, I've got an option and an argument, option argument pairs. So then on the other side of that, once I build the string, I'm going to evaluate it. I'm going to use eval-c to actually capture the output of that. I'm going to use dblank on top of eval-c to strip any leading or trailing white space, and then I'm going to send that out so that it's going to end up being a job ID. So when you spawn the swarm, it's going to echo to the screen a job ID for you, and I'm going to capture that in job ID here. And that's going to allow me, well, just for fun, to print to the screen the job number that I just spawned, but it's also going to allow me to build up a dependency string. So I'm going to come up with another argument option pair here, dependency equals after any of the job ID, and that's going to allow me down here below to set up another swarm with the dependencies that the first one has to execute before the second one finishes executing. And so you can use this not just with 2 jobs in a row, but you could do 10 jobs in a row or just whatever in order to build up a pipeline, an analysis pipeline for your jobs. All right, once I execute this, things are going to start happening rapidly. So instead of going through it step by step, I'm actually just going to work through it and tell you what it's all going to do, and then I'm going to press F5 and we're going to just run the rest of this and see it all in action. Just to be concrete, let me highlight the sprintf command, and I'm going to evaluate that selection. And that's going to print out to the screen here. This is actually the command that we're going to be using to execute the swarm. Okay. Give you a second to look that over. So we're I'm giving it once again the full location of the swarm file. -G1 for 1 GB of memory per job. I'm going to do 1 process per CPU. I'm essentially not bundling. I'm using the -B option to say don't bundle it, just 1. The partition is going to be norm, 5 minutes for each job to complete. And then I'm giving it a log directory, and that log directory is that swarm output that I just set up earlier, so that all my .e and .o files end up there instead of going into my current working directory. I'm telling it I need generic resources, gress equals lscratch, and I just need 1 gig. And then just for fun, I said that my job is going to be my awesome job. So once I execute that command, that's going to, fire that off to to Slurm, and it's going to be Slurm's problem. It's going to start running these jobs. And then I'm going to print to the screen that I did that. And then I'm going to set up that depend string that I just told you about. I'm going to open a new file, and I'm going to write 1 command to that file. And that command that I'm going to write is just going to be the 1 command for my Deer to AVI job, which is going to take all the analyzed frames of the movies and piece them all together into 1 AVI. I'm going to close that file, and then I'm going to use that second file to fire another swarm off. So, notice here that I'm using swarm to execute a single command. It's not really a swarm of commands, it's just a single command. And that's just fine. You can, swarm is a convenience, and it's just a wrapper on sbatch, and, it doesn't have any problem setting up just a single job for you. So I'm going to go ahead and use that. You could also execute an sbatch command here if you wanted to. I'm going to print that I did that, and then I'm going to jump into this other little function that I've written called monitor jobs. And so that's worth talking about. I'm going to highlight that and hit Control D, and that's going to open it up. Okay, so monitor jobs is a really, really simple little loop. It's just a while loop, and it figures out what the username is, and it essentially uses that information to call the system commands sjobs and job load, and it does so in a loop to give you information about jobs that are running. So if I call it right now, it's going to wait 5 seconds, then it's going to start giving me information on whatever jobs I've already got running. And it turns out that I only have 1 job running right now, and that's an interactive job, and that's the job that you're looking at right here, the one that I'm currently using to run MATLAB. Okay, so I hit Control C to get out of that. You can also execute monitor jobs with a job number. So here's my job ID for that job number. I could have used that as input, and then as long as that job is running, it'll update every 5 seconds and kind of give me the status of that job. So I want to draw your attention right here to this pause 5. So right now monitor jobs is checking every 5 seconds to see how your jobs are running, and I want to draw your attention to that because this is for example purposes only. This is a pretty short running set of jobs that I've got, and you wouldn't ever actually want to query the state of your jobs every 5 seconds. That's really excessive. You want to dial that back probably to 30 seconds or even more than that, because most jobs run a lot longer than these jobs are going to be running, and you don't need to necessarily be watching the state of your job every second while it runs. And in fact, there's a good reason not to do this, and that is because if you start to run, every time these commands are executed, I'm asking the Slurm batch scheduler to give me information. And so if I start to do that too much, too often, it actually starts to put a load on the scheduler. Under no circumstances ever would you want to run this without this pause here. Okay, that would be a really big no-no, and what you would be doing is basically as fast as MATLAB runs, you would be pinging Slurm and asking it for information. That's going to start to put a load on the scheduler, and at some point it might put a load on the scheduler that's large enough that you actually start to slow the scheduler down, and staff is actually going to start to look and see, what are you doing? Why do you have to ping the scheduler 10 times per second? So once again, probably you want to change this when you run your code to 30 or 60, or maybe just not run it at all. maybe just use monitor jobs to check in periodically and then close it down when you're done with it. Okay, so that's what's going to happen. So once I hit F5 here, we're going to fire off both of our jobs, and then we're going to drop into monitor jobs and start watching as these jobs execute. Okay, so let me just go ahead and do that. Okay, it spawned one job, it spawned another job, and then we've already got 58 CPUs running. Okay, so we're monitoring these jobs. You can see I've got my interactive job, which I've been running now for 37 minutes. I've got a bunch of new jobs that I just started, which have been running for about 15 seconds. And then I've got this one job here at the end. Well, then I've got an array of jobs from job number 28 to job number 299, which have not yet begun executing. They've not been scheduled. And then I've got this final job running down here, gear to AVI, which is pending. Both these are pending, and this one is pending with reason dependency. So it's got to wait for these jobs to execute first before it can run. Oh, and so we just had a whole bunch more jobs begin. So now we got 324. We've got 100. Let's see. We've got 122 CPUs, or 122. Jobs queued, rather, 154 jobs running. So these lists are going to, continue to expand, and then as more jobs are scheduled, and they're going to start to contract as more jobs start to finish. Notice here that even though I've only scheduled a single process per each job, that some of these jobs are spiking up to 100 and 150% CPU, and that's because when MATLAB initiates and when it cleans up, I think it's because when MATLAB initiates and when MATLAB cleans up, it sometimes implicitly multi-threads. So this might be one reason that you wouldn't want necessarily to pack multiple processes onto each one of these CPUs, because they might end up spiking up to 300% or so. Okay, so let's have a look back here. So if we go into swarm output, we can see our .e and our .o files here. And if I've done everything right, all of my .e files should be empty. They should all contain 0 kilobytes of data. And then my .o files, I'll open one of those up right now. And so it just has everything that would be echoed to the screen. It says that it's setting up the environmental variables, it tells me what the path is. And then on this particular job, I got a warning. It was the one that we looked at earlier. The algorithm failed to converge after 100 iterations. And that's nothing to worry about, because we're running this algorithm 15 times, so presumably on the other 14 times it was happy and converged just fine. Okay, looks like most of our jobs are finished. We have one more job that's queued. So if I look into analyzed images right now, I should have 300 analyzed images. I do. Open one up and have a look at it. Okay, that's what they're looking like. Okay, and this job that's queued still is this one that's supposed to run with a dependency, and that's the dir to AVI job, which is going to take that directory, and it's going to start putting it together in a .avi file into a movie. And so it's begun to run. And here's the movie that it's currently building. Refresh that. So we're going to start to see that this is going to grow in size, and it's not going to take too long before it's going to be finished executing. Okay, that's finished. The only job that I've got left that's running is my interactive job, and I actually gave that monitor jobs an input, and the input was the job ID from the second job. And so basically what that does is it just exits the loop while as soon as the job ID is no longer present. So that's why it jumped out of there, and then we're back in MATLAB. One thing I'm actually going to go ahead and run that again. And I'm going to go ahead and set the recompile code to false. Save it. Hopefully I don't need breakpoints set. Okay. Go ahead and rerun that. So this is just going to overwrite everything that I already did here because I'm running it again. I just want to kind of demonstrate a point here. Okay. Any second now, this is going to fire up. Okay. And those jobs got scheduled really quickly, so we already got a bunch running. My point is, if I hit Control-C now, let's see, and then let's say I open up a terminal, and I cd to Biowulf, and then I say, actually, see all my jobs are still running. So even though I Control-C out of there, and I'm not going to right now, but I could even close MATLAB, you know, shut everything down, go home, you know, fire MATLAB back up, do whatever I want to do, and these jobs would just continue to run because they're not running in MATLAB anymore. They're not MATLAB's problem, they're Swarm's problem, or to be more specific, or to be more precise, they're Slurm's problem. Okay. If I wanted to see those jobs running again in MATLAB, I can just go ahead and issue monitor jobs once again, and then I can go ahead and yeah, sometimes you get little errors with monitor jobs, so I don't know what that's all about, but usually you run it more than once and you don't have the problem again. So okay. Okay, so we can look now. So I ran it once and I had it save a movie called mymovie.avi. The way that I've written dir to AVI, it will check. Hold on. Okay. The way that I've written dir to AVI, it will check to see if the name of the movie that you're trying to save already exists, and if it does, it will append a number to it. I think that, yeah, that happens right here in order to avoid overwriting it. And then it'll check to see if the appended number exists, and if it does, it'll increment it, and it'll keep doing that until it finds a number that doesn't exist. So my point is, when the second run finishes, we're going to end up having all of our images overwritten, and then dir to AVI is going to run again, and then we're going to have mymovie1.avi in addition to mymovie.avi here. Okay, but for right now, we can just check to see what this ended up looking like. So I'll go ahead and copy this movie. Because if I try to run it from the network location, it'll kind of be jerky. And this movie is going to be a little bit jerky anyway because I'm recording, you know, for your viewing pleasure, a movie here of me doing this analysis. And so this movie's got a specific capture rate, and then this movie's got a specific frame rate, and those two things are not going to necessarily match up very well, and they might sort of alias and run into sampling issues with one another. So even though when I run this, it's going to look nice and smooth, when you view it, it might look a little bit jerky. So if you want to see the smooth version of this, you can go ahead and run it yourself. Create your own version of this by running the code that I showed you, and then you can look at this movie. One thing that you'll notice you could play around with is reduce the number of repetitions, and what you'll see actually is that the colors will start to bounce around from one frame to another a whole lot, and they won't stay constant. See how you know, my hand, for instance, it kind of changes a little bit the color of my hand with the lighting, but for the most part, it doesn't really bounce back and forth too much between different colors. If you turn the repetitions down, then you'll see that the algorithm will converge on different answers for adjacent frames, and then you'll see all kinds of, or you can, you know, change the number of colors or whatever you want to do. Okay, let's go back into No Machine. Looks like mymovie1.avi is present, so I assume that the only job that I'm going to currently be running is this interactive session, which you can see here. So I'll just verify that really quick. Don't know why that's taking so long. There we go. Okay. And that's it. So that's how to run parallel MATLAB jobs on the cluster using Swarm from within MATLAB. So if you have any questions, you can just email me at godlovedc@helix.nih.gov. And thanks for watching. I'm going to use that -y switch, that -y argument, and that's going to, either that or the -x argument, is going to allow me to continue to forward these X11 windows from one server to another. So it's going to go from the Biowulf login node and ultimately from the, you know, whatever computational resource I end up being allocated out here to Helix, where I can still see it.